Yes, so it's 11. Let's get started with the second part of our workshop. So I have the pleasure of introducing the next talk. So the next talk will be given by Frederick Rusek from Sony. And the title of the talk is The Wax Decomposition for Distributed MIMO Detection. So Frederick, I can see you're there, so the floor is yours.
Thank you. Thank you so much. So I
Yes.
will put it in presentation mode, I hope.
Yep.
How do I do this?
I'm
sorry, I don't know how to put it in presentation.
Yeah, I think it's
mode.
here. If you go, it should be one of, if you click.
Usually it is Control L, but that doesn't work.
If you right left click as you were doing before, maybe should be one of those. If you go down.
I'm sorry, but no. Is it okay like this?
I think it should be fine, and it should be fine. It's quite visible. Yes.
Okay. Okay. Good. Thank you. Okay. So my name is Fredrik Rusek. I work at Sony in Lund, and the title of my talk is the wax decomposition for distributed MIMO receivers. So we're talking about uplink MIMO receivers where you have antennas, or where you have many antennas, and you would like to have distributed reception or detection. So the motivation is that if you have many antennas, or distributed or even co-located, it may be of prohibitive complexity to actually transfer all of your information, or maybe CSI, to a central processing unit. And because of the sheer volume of data that you have to transfer. And the goal of this work is to understand what are the trade-offs between the level of complexity at the distributed units, the antennas, and the amount of data that you have to actually transfer to a CPU. So if we look at a very simple receiver, this is, I guess, the simplest architecture that you can assume. Though you have K antennas or users, and what is actually important for here out on the user side is how many spatial layers are you transmitting. So I say K antennas, but it actually means how many data streams are being transferred in the uplink. You have a receiver, an AP, having M antennas. Each one is receiving one complex number in a narrowband system. So the mth observation can be expressed like this. X is whatever the users are transmitting, and H is the channel vector here, or HM is the channel vector from all of these users to the mth antenna. And the simplest receiver, the normal one, is that you take your observation. If you are an antenna, you take your observation and you pass it on to a CPU. So the incoming signal here, Y, would just read the familiar MIMO equation, Hx plus N. The issue is now that if M is super large, then then you have M observations here, which is a big vector, and you have many subcarriers. So the data rate or transfer rate that you have to provide the CPU with, it can become prohibitive. Another completely normal receiver is to rely on MRT, on MRC at the distributed units. So before you are transferring your observation, if you are an antenna again, then you pre-multiply by a vector. This vector here is the observation that you have made. So essentially, each antenna have to perform channel estimation, and then you are weighting your observation with the observed channel vector. So here you have K outputs. If you have K antennas out here, and then you sum it all up, and you pass the combined sum to a CPU. So this is called I mean, normally called a filter receiver. Equation-wise, the vector R here is nothing but this familiar equation. So H Hermitian here is the match a filter that you have applied. And what is interesting here is that the mutual information between the vector R and the transmitter vector X, it remains the same as for the little bit simplified receiver here. So the mutual information between Y and X equals that of R to X. So you have lost absolutely nothing if you implement the right-hand side receiver. So if we now compare the two receivers here, so we can see first of all that the mutual information is optimum. So both of them allow for optimum detection. If we count how many inputs do we have here at the CPU, so for the simpler receiver, or let's say conceptually simpler one, you have M inputs to the CPU. The other one, then you have K. And K being the number of UEs, or UE antennas, or spatial data streams. So how many, and then you can see how many antenna outputs do you have? How many outputs or data or symbols does each antenna have to, let's say, output? In the first receiver, it is only one, namely the observation itself. The second one, it is K. Because you are multiplying here by a vector that is of dimension K. If you now count how many multiplications do you have to do per antenna, in the first one it would be nil, because you are only passing through your observation. Here it is K, because you have to take the observation and multiply by this vector. And what do you have to do at the CPU? You basically have to do the, let's say, detection, if you have an LPC code or whatever. So you have to do some stuff here. You have to actually now decode or produce LLRs or whatever. So if we then plot what we just had in the table, and then the left-hand side here is how many outputs per antenna do we have, and how many inputs to the CPU do we have. So the conceptual simplest receiver, it has one output per antenna, and then the CPU has M inputs. The other one that may be a little bit more complicated, or at least appear to be a little bit more complicated, has K outputs per antenna, but it only has K inputs to the CPU. So we know that we have the two operation points here for those two receivers. If we now look at, let's say, if I'm not so interested in the number of antenna outputs, I am a little bit more interested in how many multiplications do I have to do per antenna. Then it would just be that the first receiver has just zero multiplications. The second one has K. So this is an overview of how the operations between the complexity at the antenna units and the complexity on the, let's say, front hall of the CPU, they are looking like. Huh? And then the problem formulation is basically that we would like to not maybe operate always either here or here. We would like to understand where can we operate and still be optimum. It is very simple to see or understand that it is absolutely impossible to work with lossless processing if you are in the red area. It can be understood fairly quickly if you sit down and take a look at this. So you simply cannot feed the CPU with less inputs than K, because you have K users, and you can clearly not allow one antenna output. But the question is, where can we operate in here? So maybe it would look like this. And when I say, if I say where can we operate, I am asking for operate with optimum, with optimum and mutual information. So clearly, I can operate in the red, in this red region, but I will not be optimum. So I am asking for where can I be in this picture and still having an optimum receiver. So it is a trade-off between how many inputs to my CPU do I have and how many antenna outputs do I have. And basically, we only know in advance 2 points. We know the normal receiver or the standard architecture where you are just passing on your observation. And we know this MRC receiver that is now down here. But we don't know the, let's say, how this boundary looks like. It could, for example, look like this. We don't know. So we have now 5 questions that we would like to have answered. We have more, of course, but I will look at these 5. So first of all, what does it mean? How does a receiver or a receiver architecture, I would say, how does it actually look like if we are operating somewhere here? It's a little bit weird because it is conceptually straightforward to understand maybe this point and that point, but it is not a little bit less so if you're are now anywhere in this region here. Of course, we're interested in understanding where is this boundary, what points are actually achievable if you want to have optimum rate. We want to understand how much rate is lost for the optimum receiver if you are down in the red area. And then we have some extensions. I don't think I will have time for those, unfortunately, but we will see. So we can now address the first question. How is the architecture of a receiver actually looking like if we do not have one of these 2? So if I don't have this one, the conceptual simple one or the MRC one, then what is it I should do? So we look for similarities, and we can see one thing here, that if you now look after this vector multiplication here, you have k outputs, and then you are summing up here. So that is what is happening, but I can actually write these k outputs and the vector multiplication in the let's say simple receiver. I can express my output here as the input multiplied by a vector of length 1, and the vector happens to be just 1. So this is how I can. I mean, I have changed absolutely nothing. I can also express or insert a matrix here. And I take the identity matrix, because if you think about this, if you take all those inputs and you multiply by the identity, you still have identity. So by just introducing these identity operations here, we have almost, let's say, unified these 2 receivers. They have different parameter sizes and so on, and they have different matrices, but they look almost the same. So what we now can do is that we can say that, okay, in general, if I would like to have L outputs from each antenna, I will multiply by a vector having length L. So then we have, let's say, a design parameter. It is this L. How many outputs do we have per antenna? And we can specify this now L. And then instead, as we had here, having an identity matrix or a summation matrix, I can have an arbitrary matrix here, A, and I call it A Hermitian for reasons that will be clear a little bit later. So the number of CPU inputs is given now by the dimension of this matrix A. Or A Hermitian. If A Hermitian has T rows, it implies that my CPU has now T inputs. And the number of columns of my A Hermitian has to be the number of antennas M multiplied by the number of observation or of outputs per antenna L. So now my receiver architecture will be this according to what we have on the screen now. And what remains is to say, okay, or to specify, and what is the W, and what is A, and when is it optimum? You know? And so here is just a small example. If we have the MRC receiver, this A Hermitian matrix looks like this. It is just summing up, let's say, different. It is only summing up different vectors. Or the absolutely vanilla architecture, it is just our identity matrix. But what we can see here is that the matrix for those two cases, the corner cases, they are actually deterministic. They are fixed. They never change, no matter what the channel is. The matrices, they stay the same, and they are comprised by zeros and ones. And now, and what we will do now is, of course, now we will try to preserve this condition of A, that it is 0 and ones and never changes. So if we just take a illustration of what do we have actually at the input of the matrix A Hermitian. Then we have all our observations Y, and they get multiplied by a big matrix here, and you can carry out this multiplication antenna per antenna, because let's say Y1 will hit some numbers here, W's, but all of this is calculated at antenna 1. And then you have the output of this big matrix multiplication here, which is written W as W Hermitian Y. It's input to A Hermitian, and out comes this set, and set has exactly T coefficients or dimensions. And we still don't know if I can have any T and any L. Let's say we don't know what L and T L and T combinations that are permissible from a mutual information perspective. Then we have the result here. It is a little bit cluttered. I have a cleaner form soon, but I chose to have it like this. So if we now have integers L, and L means the number of outputs from the antennas, and we have T, the number of CPU inputs. And then we have a matrix A that is fixed, and fixed means that it will not change depending on the channel. So the result here is guaranteeing existence of a matrix A that is not dependent on H, the channel, meaning that you can implement it once and for all. And then it exists a block diagonal matrix W, meaning that it is representing the antenna processing. It means I can find these antenna weights in such a way that I will be mutual information optimum. And this exists if and only if I can find a matrix X Hermitian that is representing the CPU processing in such a way that I can express my overall channel matrix as a matrix product. So without all of this cluttering, it says here that if I have given L and T, that is the number of outputs per antenna and the number of CPU inputs, I am able to find and I have a given A, I can have rate optimum receptions if and only if I can decompose the overall channel matrix like this. So W is block diagonal, or should be block diagonal, and depending on the H. A is fixed, it never changes. So you take an A and you hope that you are able to decompose your channel matrix H according to this equation. And X is absolutely free. There are no constraints because X is now something that is happening at the CPU. Yeah, so this is what the result is saying. So if you have T and L and a given A, and T and L are specifying dimensions of all of these matrices, it is possible to have rate optimum reception if for any H I can find such a block diagonal W and some X. Yeah, okay, so here is just a repetition of what I said. And rate optimum performance can be achieved if and only if I can find a matrix A so that all channel matrices can be wax decomposed. And the wax decomposition follows from this structure, the naming of it. Yeah, so if I can find an A so that for every single H, I can find block diagonal W and X. I know that I have found an architecture of a receiver that is actually lossless. Okay, so now we can ask, okay, for what parameters, meaning T and L, is it actually possible? So, and that means so that when is the wax decomposition, say, possible to actually carry out? And then we have a little theorem here. So if you and it will be sharpened I mean soon. So if you take a random matrix A that is complex, so it is not 0 ones, it is just random. You just pick one, and you take any matrix H except those of the set of measure 0, meaning that you can find counterexamples, but they have measure 0. And then you can always do this wax decomposition if and only if the number of CPU inputs is now fulfilling some condition here. So it means that if you want, if you have 100 antennas M and you have 10 UEs K, and instead of having 100 inputs, I want only 40. And that means that you can calculate the number L, which represents the number of outputs per antenna. And then you can pick any A. You can just randomly generate an A and it will work. You can always find this W matrix and the X matrix as a CPU so that you have lossless perception. If you now visualize it, the green area or this equation here, it will specify a polygon that looks like this. And what is very interesting here is that even if you only have one output per antenna, it is possible to do better than feeding all your observations to the CPU. So if you now recall the conceptually simpler receivers, where we started, it had one output and n CPU inputs, but you can actually do better. You can reduce this a little bit. So here is where we are. So in the green region, we are able to operate lossless. In the red region, we are not. It is just not possible. And then you can ask, okay, I said that you can pick an arbitrary A, but I would actually like to have not maybe a complex valued A. I would like to have clean, maybe 0 and 1 only, and it should be sparse because I have to implement it. We don't actually know what A in general. We don't have any sufficient conditions for what A, but what we do have is that if you take an A that you would like, a 0, 1 A, maybe, lots of zeros, lots of ones, and you take a random H, and if it is possible to perform the wax decomposition for this random H, it will be possible for all H. So it is extremely simple to figure out if my matrix A is valid, if it allows for wax, because you take any random A, you try to perform the wax decomposition. If you succeed, then you know that for any H, any channel that you will ever face, you can always do the wax decomposition. So here is basically a little recipe. You take A randomly. You would like to have it sparse and 0 ones. So you just generate one. You generate a matrix H. You try to do the wax decomposition. If you are successful, then you have found your A. Otherwise, you have to regenerate another one. So here is a picture on sparsity of this matrix A. We would like to, of course, have A to be 0, 1 matrix. We have 100 antennas and 10 UE antennas. And here is the percentage of ones in the A. And it is possible to find a matrix having, around 10% of ones, and the rest is just zeros. And if you take such a matrix, it will be okay with 1% probability. So you have to try maybe 100 times. But after having tried all of this, then you have found your A, and you never have to change it again, because it is a deterministic matrix that you can build into hardware. So A never ever changes. It is only the W, the antenna processing, that will actually change. So here is just another numerical result. And here is we have L here and K, number of users, number of antenna outputs. We have M60, and then you ask, okay, to implement the matrix A in hardware, how many 2-input sum modules are actually required? And it is the same number here. So to implement this matrix A in hardware for this numerical case, you need about 55 summers, or 2-input sum modules, and then you are done. And I have 3 minutes left, so I will just quickly go over that you can also do this on panels. So let's say that you have now distributed panels. So each panel is receiving n observations. In that case, it is still so that you would like to give L outputs, but now you have, instead of a vector here, you have a little matrix of size L times n, because you have n antennas and you want L outputs. So you multiply by some matrix. You have this compression matrix here that is again fixed. And the same story. We know what L and T's that are working here. But now the number n is now important, and the matrix A is being generated as a sparse matrix, and 0 and 1s, and you have to try it out until you get something that is working, and then you have found it. And here is a numerical example of the wax decomposition. Here is the original channel matrix. It is an 8x5 matrix. In this case, we set L to be 2, because the W here is now 2 by 2. And here is an A matrix, and this will never change. So what the wax decomposition is, it is a new matrix factorization that works as follows. The A part is fixed, so no matter what H is, A remains the same all the time. And then it is a decomposition method of finding a block diagonal matrix out here and a free matrix here. So for a new H, a new channel matrix, A is fixed, and you update this part and you update X. And the existence of a wax decomposition, it guarantees that you have optimum performance. And I think my time ran out, but I was basically done. Anyway, so my summary is just that we have developed a new theory for a trade-off between the number of antenna outputs and the number of CPU inputs. There is this trade-off. There is a very simple formula that will state exactly how many CPU inputs that is actually required. And it all relies on a new matrix decomposition that we call the wax decomposition. And that was my half hour.
Okay, thank you, Frederick, for the nice presentation. Any question or comment to Frederick? Seems no. Maybe just a quick question myself. Maybe I didn't really get about the X. So I understand that this A is something that you define and then you can implement on hardware that is always the same. W depends on the channel. I didn't really get how you design this X. You said that this is
No.
free or?
Yes, I mean, the result states that you have lossless performance if any H can be expressed like this. And the W sits out at the antennas and have a structure. It is block diagonal, for example. A is whatever, and X you can pick. So an X is never actually needed. You don't need X, but you have to guarantee that you can decompose the matrix X, the matrix H like this. But X will never be actually computed by the receiver. But you only have to guarantee that I could do it if I would like to.
Okay.
But it will never be actually used.
Okay, I see.
Okay.
Okay,
so thank you so
you.
much.
Thank you, Frederick. So I think now we can move to the next part of the workshop. So I leave the word to Sergio for introducing the next speakers.
Okay, so can you hear me?
Yes, we can.
Okay, so greetings from Portugal. It's a sunny day, so hope we can enjoy the rest of the workshop. So here I'm replacing Luis. Unfortunately, was not able to come at last minute, but I'm also involved in TERRAMETA project. So I'm leading the one of the work package related to hardware. So now I have the pleasure to introduce my colleagues that have been working a lot on hardware. So TerraMeta is a project that focuses a lot on developing new hardware solutions for terahertz, which is, as you know, a big challenge. So the first presenter is Antonio Clemente. He's been one of the leader researchers on transmit array, configurable transmit array, with a wide range of applications since from X-band to terahertz more recently. And I think he will be the perfect person to present this work on the overview from the technology, classical technology for configurable transmit arrays to now the more recent microelectronic options that we have. So, Antonio, go ahead, please.
So thank you. Good morning, everybody. Can you hear me? Can you see my screen? Yes?
Yes.
Okay, perfect. So thank you very much, Sergio, for the nice introduction. Thank you very much also for the organization of this workshop. So in this presentation, I will talk about some limitation on classical architecture based for the reconfigurability of the reconfigurable intelligent surface that are typically based on pin diodes. And I will explain how new technology can be used to develop new architecture up to sub-terahertz frequencies. So this work has been, as Sergio said, has been realized in the framework of the TERRAMETA. We have also some small contribution from another project that is the French recovery plan, Sistera project. Opla. It works. Okay. So in the TERRAMETA project, we are developing in one of the proof of concept. We are developing a full D-band point-to-point link demonstration that merge the technology that has the radio frequency technology that has been developed in Leti in the last years. That you can see here. I will explain you after in the other slide what is this kind of device, and we integrate a baseband unit platform, a commercial one from Intracom. So you can see are the baseband unit 1 and 2 for the transmitter and the receiver. And after you can see that there are two different devices, the transmitter and the receiver, radio frequency devices, that are based on an IC that we developed in Leti that is integrated on a specific packaging based on printed circuit board. This IC, this is the transmitter, but we have also the receiver in a similar technology. It's integrated on a first antenna that is an array of 2 by 2 elements that illuminate a transmissive wrist, so a transmit array. So basically, this is a flat lens that is composed of different unit cells that are the element that radiate the energy and at the same time generate a phase control on the aperture. So each element of the array in this version is a passive antenna, so there is no electronically phase control, but we can control the phase gradient on the lens, on the flat lens, by controlling only the inner layer of these three metal layers lens. So you have two polarized grid on the top and bottom layer, and in the middle you have a rotator. So by changing the shape of this rotator, we can generate a specific phase level, and after we can distribute these phase levels on the lens, and we can generate a phase control. So you can see here an example of this lens, where in the inner layer you have different rotator with different shape. So each one of these elements correspond to one of these phase level. So in this case we use a 4 bits phase control, 16 different phase levels. Now, in European Microwave Week last year in September, we showcase a specific setup where we integrate as well as a robot with camera from Dell Technologies. So the full demo you can see here, the full demo that integrates the radio frequency part from SEA, the baseband part from Intracom, and the robot from Dell Technologies. So what we are doing now, as I said before, the transmissive wrist that you have on the top of our demo is a fixed beam. What we are trying to do in the last period of the TERRAMETA project is to find a way to perform reconfigurability on the wrist. So how it works a transmit array or a transmissive wrist, a moment. So we need to electronically control the phase level on the different unit cells. So in this case, we replaced the pin diodes with LEDs in order to show how we can electronically control the level on each unit cell. So in this case, we use a 1-bit phase control. You have only 2 colors. So typically, this kind of phase control can be achieved by considering pin diodes or MEMS switches or varactor. So, but if you see, this classical technology can be used in a millimeter wave frequency band, but are very limited if you would like to go in frequency up to 300 giga. So if you take a look in the state of the art, the current state of the art, several technologies are studied today in order to generate reconfigurable intelligent surface at sub-terahertz frequency. Between the different technology, you have the possibility. You have, for example, CMOS technology. So basically, the RIS has been developed directly on the IC, on a chip, on silicon. Or you can also use phase change material to control the level of the phase on each unit cell. This work is as well as a demonstration of a CMOS reflect array And more recently, there are also people that are working on Schottky diodes. So the limitations, so basically the solutions that are today available that are based on CMOS technology present very high losses. For example, the second work that you have here present more than 15 or 20 dB of losses, so it's very high. You cannot use this device as an antenna. You need a power amplifier to mitigate the losses, and also the CMOS based transmissive risk that you can see on the top cannot be controlled independently all the unit cell. So the same for the PC, for the demonstration of the PCM. This is in reality is not a reconfigurable one, but they generate different layouts, each one with a different phase control, but you cannot do this reconfigurable in real time. And the same for the Schottky diodes. As you can see here, you cannot control you have only one line, one bias line for each column. So you cannot control independently the phase of each unit cell. So basically the phase control is limited. That's what I wrote here, that today there are some demonstration of the technology, but you cannot have a full control of the reconfigurability of the surfaces. So in the TERRAMETA project, we are studying, especially in the work package led by Sergio Matos, we study different technology to develop switches that can be integrated on the metasurfaces. Basically, we studied the possibility to use pin diodes up to sub-terahertz frequency, MEMS, varactor, liquid crystal, phase change material, Schottky diode, CMOS, memristor, and microfluidics technology. So in my presentation, I will more concentrated on the activity we done in my team, more on phase change material, Schottky diode, and CMOS. I think that in the last workshop in last year, I presented some results on phase change material, so you will have an update of this work today. So typically, as I said before, when we do a reconfigurable transmit array or transmissive metasurface, what we done, we integrate switches on the top of a metasurface, that a metasurface composed of several unit cells. So in this case, it's a 24 by 24 element metasurface. On each of these elements of the metasurface, you have 4 pin diodes. You have 2 pin diodes on the top level and 2 pin diodes on the bottom level. By controlling the pin diodes, we can generate a beam control, a reconfigurable beam control, as in this case. So when we take a look on the different architecture that we can use in the frequency band up to 40 giga, you can see that we have we can increase the complexity of the unit cell. So this is a unit cell of the metasurface that I presented before. The periodicity in this frequency range vary between 10 millimeter up to 5 millimeter, even a little bit less. So in this case, this is a 28 giga, we have a periodicity of 5 millimeters. So to achieve a 1 bit of phase control, we need 2 pin diodes. If we need to increase the number of phase control, we need to add additional pin diodes. So basically, for a 2 bit of phase control, we need 4 pin diodes. And if we need to control electronically the phase and the polarization of the metasurface, what we can do is stack different metasurfaces, as in this case, with a major complexity, because we need to add additional pin diodes only to control the metasurface. So as you can see here, this is an extraction. This picture has been extracted from the CAD model. Is the real dimension. There is a zoom, but this is the real dimension of the different component by considering the periodicity of 5 millimeter. As you can see, the packaging of the pin diodes is quite big, quite large, if compared to the size of the radiating element. So when we go up in frequency, we will have the dimension of the radiating element will be smaller, and it is not possible to integrate this kind of device directly. For this reason, what we are studying are a new solution to do this. So the first important part to study is the possibility to use standard packaging technology or new packaging technology to realize this kind of antenna. So firstly, we started by studying the possibility to use standard printed circuit board technology to develop metasurface up to 300 giga. So this is a demonstrator we done 2 or 3 years ago, where we demonstrate a very large transmit array operating at 300 giga band and with a very high gain. So we demonstrate for the first time the possibility to use this kind of technology with PCB to achieve very high gain a sub-terahertz frequency. The question now is it possible to integrate on this kind of structure the reconfigurability? So firstly, we started to study the possibility to integrate pin diodes in order to study the limitation in frequency of this kind of device. So we developed during the TERRAMETA project this kind of structure that is a unit cell for a reflective RIS, is not a transmissive. Why we select this kind of structure? Because in the case of reflective RIS, we need only one pin diodes to control a 1 bit of phase resolution. As I presented before, in the case of transmissive RIS, we need 2 pin diodes that are the minimum number to achieve a 1 bit of phase control. In the case of reflective RIS, you need only 1. So for this reason, we start to do this design, and we demonstrate this unit cell that can operate on 2 different frequency bands. So the frequency band between 60 and 75 giga, or in the frequency band between 100 110. Okay, so by controlling, so here in order to generate the 2 frequency beam, we have 2 different horns that illuminate the metasurface. On each element you have 1 pin diodes, and we can generate a phase control on two different frequency band, and we can also generate a beam steering in these 2 frequency band. So, but for us, this kind of demonstration is maybe the limits of the use of pin diodes. So we cannot go up in frequency, and as I said before, it will be very hard to add additional pin diodes on this kind of structure. For this reason, in the TERRAMETA project with our colleagues, with the ACST group, we are studying the possibility to use new device such as the Schottky diodes. Why we select this kind of structure? Because if compared to the packaging of the pin diodes, the Schottky diodes are very small. So can you see? And we think that we can integrate easily this kind of diodes in our devices. So we developed. So in this work, I presented only the transmissive RIS, but we are developing with Sergio and other colleagues also the possibility to have a reflective RIS with Schottky diodes. So in these cases, this is a transmissive RIS. So the transmissive RIS use only a PCB with 2 metal layers. On the first layer, you have a polarized grid. On the second layer, you have the unit cell. You can see that there are 2 Schottky diodes for each unit cell. You can see even here the dimension of the structure. When we simulate this structure, you can see that this metasurface can operate in the frequency band around 100 giga, and we can achieve a 1 bit of phase control, reconfigurable. The next step is the fabrication of this structure. But firstly, what we are doing now, we are developing the electrical model of the diodes, and at the same time we are developing the technology to flip chip this structure on the unit cell, because as I said before, this Schottky diode is very small, so it's only 300 micron by 200 micron, and the thickness is less than 10 microns. So we are developing a new thermocompression procedure to flip chip this kind of structure. And I hope that for the end of the project, we will have a real demonstration of this setup. So in parallel to this, we are studying the possibility to develop new packaging solutions that are based, for example, on fused silica. So you can see here a transmit array we develop in collaboration with other partner, external partner, that is the University of Rennes, UTR, Professor Ronan Solo. We demonstrate recently this transmit array that operate in the frequency band around 280 giga. You can see here the measurement and the simulation that fit very well. I will explain you after this. While we are studying the possibility to have a glass solution, so because the fused silica has electromagnetic properties that are very close to the PCB, with an epsilon R that is close to 3-4 and very low loss. So typically this kind of material is very good for the demonstration and fabrication of metasurfaces, but at the same time is very fragile and is very hard to have vertical connection inside the glass. So why we would like to use this kind of material? Because on this material we can easily, so this material is also compatible with clean room process. This is not the case of a PCB, of printed circuit board, but the fused silica is compatible with clean room facilities and process, and by using this kind of material, we can integrate on the top of that phase change material. We can directly print phase change material on also memory store in reality. So what is a phase change material? With a phase change material, we can, by heating a particular material, for example, germanium telluride, as in this case, when we apply a thermal control on this material, we can change the properties of the material from amorphous to crystalline and vice versa, and we can generate a switch. Okay, by controlling thermally this kind of device, we can generate a switch and we can generate a phase control on the transmissive wrist. But as I said before, we are developing the full packaging technology because we need vertical, in a particular case of unit cell, we need vertical connection, and we integrate on the top of this transmissive wrist two different switches that are based on this kind of material. So the main part of the work in TERRAMETA is the study on how this vertical connection can be developed. So for this reason, to study this, we developed several passive transmit array. You can see here the mask of the transmit array on the wafer, on the glass wafer. So you have 4 different antennas that generate a different phase control. For the moment, there is not phase change material on the top, because the first level is to study the possibility to have this vertical connection from, so you have 2 different wafer of glass, a ground plane in the middle, and a vertical connection from the top to the bottom, where on the top and bottom you have 2 different radiating elements. And what is important is to guarantee this vertical connection with a continuity of the metallization from the top to the bottom. So this is not very easy to do. You can see here the first step of fabrication and the second step. So now we are waiting for the measurement of this kind of setup, and I think that for the end of the project we will have the demonstration of this kind of structure. Next step is the integration of the device for the reconfiguration. So the first demonstration we think will be in the next months, but not based on phase change material, but in collaboration with other colleagues from Nova and ET from Portugal. We are developing this kind of structure based on memory store. So you can see an example of reconfigurability from simulation by using phase change material. So I hope that in the future we will have this kind of demonstration in practical as well as. So the last part of I have 5 minutes. In the last part of my presentation, I will present another possibility that is an hybrid solution. So I presented standard PCB technology as a packaging, glass, and now an hybrid that is based on PCB and silicon packaging. So as I presented in my first slide, I don't know if you remember in the beginning of the presentation. So this, in our demo today, we use a metal surface that is based on 3 metal layers. The full structure today is passive, and in order to control the phase, in the middle metal layer, we change the shape of the unit cell of the metal surface to control the phase. The idea was, the question was, is it possible to generate a phase control in the middle layer by integrating an IC? So to this purpose, we study firstly the possibility to have this hybrid packaging where you have 2 PCB and an inner layer on silicon HR, high resistive silicon. Because the idea was to integrate in this inner layer the rotator and the switch technology. And you can see here the IC we are developing. We developed in reality. So how it works, this kind of unit cell? So on the inner rotator, if we can integrate different switches, for example, 4 in this case, what we can do by controlling the phase, the switch element, the 4 different switches, we can generate or a transmissive metasurface or a reflective metasurface that operate on both D band and 300 gigaband. So you can see on the top, you have the transmission magnitude of the unit cell and the phase of the transmission coefficient. On the bottom, you have the reflection coefficient and the reflection phase. So in both cases, we can achieve a transmission or reflection with very low losses, and we can generate a phase control of 1 bit. So even in this case, we demonstrate first design that are passive without switching, only by having open circuit or short circuit. We demonstrate the possibility to have both transmissive or reflect array. We compare to the simulation, and we have a first demonstration of this concept. So you can see here the peak gain in broadside direction, comparing by measurement and simulation, and radiation pattern generated by this structure. Now, how we can integrate the switches? So basically, we develop this kind of packaging, as I said before, with an hybrid technology between PCB and CMOS. On the CMOS, we integrate all the reconfigurability. And you can see, I cannot show everything of this unit cell because we are under patent process, and I cannot show everything. But basically, you have 4 different switches integrated on the IC. By controlling the state of the 4 switches, we can generate transmissive control or reflective control, as you can see here. And we design the full IC. In reality, in the IC, you have not only one antenna, but you have an array. You have yet a subarray. So at the end, you have a tile technology, and we can integrate different IC in the PCB to have a scalable metasurface. So in the IC, there are 5 by 5 elements on each IC. And what is nice in this kind of IC, we can directly integrate in the bottom, you can see here, this is the logic circuit we use, the memory, to control the full IC. So at the end, we need only the DC control for the DC voltage, and all the memory is directly integrated in the IC. So this is the last slide. Several technology are today studied to implement reconfigurable metasurface in the sub-terahertz frequency band. Among this structure, we are studying the possibility to use different RF switch, such as memristor, Schottky diodes, phase change material on CMOS technology. And we are also developing different solution for the packaging technology. Why we are doing this? Because we are trying to develop the best technology with the best trade-off between phase control, technology maturity, insertion loss, bandwidth, power consumption, switching time, etc., etc. So I would like to say thank you to all the partners and all the colleagues who are working on this on the study presented in this presentation. So if you have any question, I'm here to answer. Thank you very much.
Thanks a lot, Antonio. And so the paper is open for questions. I guess I have to see some raising hands here, so someone is okay. A bit quiet. So maybe I can do a first question, maybe a more general one, because so we are working in alternative technology to phase arrays. However, the phase arrays are the standards, right? Yeah. So maybe you can, because I know you are the right person when we want to know everything about the state of the art. Maybe you can overview a bit what are our challenges and why we are going a bit against this phase array trend, and then we have a question from here. But
yeah, so the reason why we think, and that's a lot of people think, that the metasurface are a good solution or are a good how I say a different solution compared to phased array is that on the so in the metasurface you have not the feed the power division on the feed network, but you illuminate spatially the metasurface or also by considering a surface wave. So in this way, this feeding mechanism can reduce a lot the losses, especially when we go up in frequency and when we need to achieve a very high aperture, a very big aperture. So this is the first reason why we can use metasurface and not phased array. The other reason is that in the case of phased array, as I don't know if all people know how a phased array is implemented. You have an antenna that can be realized on different packaging, such as PCB or other packaging, and you need to integrate an IC, as you can see here, for example. So you have an IC on the lines of the antenna. The main problem of this kind of structure is that the pitch of the IC should be the same than the pitch of the antenna. And when you go up in frequency, there is a very big limitation on this. So for this reason, another problem is this. A last problem is also that the phased array control the phase. So you need to implement on the IC phase shift device. The phase shift device can have a very high loss. And to compensate this loss, you need to integrate an additional power amplifier layer only to mitigate, to mitigate these losses. So you will have a structure that will be very lossy, and you need to add an active device to compensate the loss. You will have more power consumption. So for me, this is the reason why.
Yeah, thanks a lot, Antonio. It clarifies a lot. So there is a question. So
yeah, from Guillaume, I think.
Yeah, can you go ahead.
Yes, thank you, Sergio. So thank you very much, Antonio, for the talk. Very interesting. I have a question related to the bandwidth of the device. Can you comment a bit about that?
So you can see this device when it's passive. The advantage of this kind of structure is that you can achieve a very wide bandwidth. Okay.
Yeah.
The unit cell, but the total bandwidth of this device depends as well as from the illumination. Okay. So when we increase the size of the antenna, due to the fact that this is not a true time delay device, the bandwidth vary between, I think, is more than 10% in any case, but you can achieve between 10% up to 30% as well, as you can see here, with very low losses. So this is the case of passive design. Now, in the case of pin diodes, we can achieve as well as up to 50% of bandwidth on the unit cell, even a little bit more. We have also a demonstration of a 1-bit unit cell that operates between 24 up to 31 giga. So this is a very wide band, it's around 20%. The limitation after can come by considering the illumination of this structure. For this reason, we are working also on near field illumination of this kind of structure. So here you can exactly see what I said before. When we increase the size of the structure, even if the bandwidth of the unit cell is very huge, due to the fact that the illumination and you have no true time delay control, you reduce a little bit the bandwidth. So this is the prototype that you have in your lab that I shared with you. The bandwidth is around, I don't know, 10%, I think. Okay. In the case of reconfigurable device, when we use the same philosophy than pin diodes, is the same. You can have up to 20% of bandwidth, as in this case. But when we start to use CMOS technology, so I forgot to say you that this technology is the RF-SOI 45 nanometer from Global Foundry. So the switch, the typical switch in this technology cannot operate at 300 giga. But we are using a specific architecture to increase the frequency of operation of this device. For this reason, we have the bandwidth, the total bandwidth is narrow. So, but even in this case is more than 5%, is around 8%, 8-9%. Okay.
Okay. Okay. Thank you very much. Yeah. Thank you.
Okay. We need to move on to the next presentation. So it will be done by Professor George Alessandropoulos from NKU, University of Athens in Greece. So he has been leading a lot of the literature and even with dissemination and with the standardization activities related to terahertz. And he's been our project manager, so a technical manager for TERRAMETA. And he will for sure give us a great presentation about beamforming and channel characterization at terahertz. So go ahead, George. Thanks. Oh, you are muted. Sorry. Yeah.
Sorry. Can you hear me now?
It's a bit not clear here. The microphone, maybe.
Can you hear me? It seems that today I'm facing some issues with the mic.
Yeah, the mic is not very clear. I don't know if you can do something, but maybe you can follow anyway.
Okay, let me share my screen as well. I will try also to speak louder. Tell me if you see my screen. Of course, not my desktop, but you need to see the master slides. Can you see them?
Yeah, we can see. The sound is not the perfect sound, but you have a strong voice, so probably we'll manage.
Yeah, I will do my best to speak loud. So you see that I'm changing the slides, right? Everything can be seen. Okay. So Sergio, thanks a lot for the introduction. Welcome everybody. It's a pleasure being here to represent TERRAMETA, actually the other major pylon pillar of this project, which is signal processing techniques for actually running those fabricated RISs at those frequencies that actually Antonio very well presented just before. So let me use full screen and go direct to the actual focus of my part, which is on channel characterization and beamforming design with RISs in general, and I will spend some time going through a bit of, let's say, discussions around this technology, the different types of RISs that are available out there. In my part, I will actually touch mainly on the conceptual level of different architectures, hardware architectures for RISs. Antonio actually described in detail certain things that are happening not only within TERRAMETA, but also in the different of RISs. So due to, of course, all the projects presented before, mainly from Times and TERRAMETA, we know well that terahertz frequencies have a huge potential in certain use cases. Initially, we hoped for 6G. 6G seems to have abandoned terahertz, but hopefully it will come up in certain use cases. And I want to emphasize here these use cases that we are working with within the project is ultra high data rate backhaul and X-haul links, but also high capacity links when we're talking about short range communications, but also enabling different applications than communications like sensing and radio mapping, especially in indoor industrial environments, which is one of the major core use cases that we have within the project. On terahertz frequencies, we have this abundant bandwidth, but we have this severe problem of path loss and the limited diffraction, which actually necessitates highly directed links, and this is exactly what we're trying to do with using RISs, which are an energy and cost-efficient technology for overcoming coverage limitations through intelligent waveform control, and we will discuss it today. So these are the main, the core components of a configurable intelligent surface, which is comprising of a panel, a 2D structure, usually comprising of discrete unit cells whose properties can be dynamically tuned according to certain objectives when we're thinking about incorporating a metasurface within the network. And there is, of course, a controller, which is, let's say, the back-end part of this metasurface, which is responsible for two major functionalities. The one is, of course, to tune the states, the different states, the different responses of the unit cells according to certain objectives that we have. And usually, these objectives are actually accompanied from the network. So this controller needs to be the interface of the actual metasurface with the network. These are two very critical things. Mainly the first part was covered by the discussions before with the previous speaker, Antonio, about the different technologies of realizing these unit cells. In TERRAMETA, we have been really interested on 150 and around 300 kind of sub-terahertz frequencies, right? But there is also the other part which has to do with how we actually run algorithms fast and efficient, and how we incorporate it in the network. There have been actually various works, and this has been one item that has been discussed within TERRAMETA of how we actually optimize the metasurface and which are the ways to do it. One way, for example, could be to try to estimate the channels where the RIS is involved, and then using this channel knowledge to run our algorithms. The algorithms then will output the configuration of the RIS, set it, and let it play. The problem is that when you have RISs, especially with those envisioned very light hardware, you don't have the capability, at least in the conventional, the first proposal of RISs, to do certain estimation at the metasurface side, which means that you have to estimate those channels that are functions of the configuration of the RIS at the receiver side. And this, of course, entails certain overhead in order to be achieved. Another way to do it is by using, let's say, predefined phase responses, phase profiles of the metasurface, and when you want actually to achieve a certain objective, to try to sweep over these predefined profiles, that it would be wise enough to, let's say, to design them in structures that are easily and accessible when you want to run an algorithm. For example, we could think of these hierarchical code books that we have in conventional minor systems, where in much faster ways than using narrow beams, we actually transverse the code book in order to find the right configuration. So with this RIS, there has been this notion of smart wireless environment, where, as I said before, you need, together with all the other RAN components, to try to orchestrate those meta surfaces to achieve certain objectives. One objective, this has been discussed by Antonio before, or enabling actually an end-to-end debug link. This was presented in European Microwave Week in 2024. With this high bandwidth, this 57.6 gigabps debug link, by using both a fabricated reflecting wreaths and the transmissive wreaths that Antonio presented before, use both at the transmitter and the receiver side. The very interesting thing, though, with the metasurfaces, and this was very relevant to the last part of my presentation today, is that you can also think of other ways of using its capability, and there has been a lot of activity from the research community lately of trying to think of metasurfaces as ways of efficient means, actually, of realizing computations over the air. Here in this, one of the first papers elaborated on that, the goal of actually trying to shape the channel impulse response in a scenario where you're having inter-symbol interference, and instead of, let's say, doing all the sophisticated IC cancellation stuff at the receive side, you're trying also with the metasurfaces to change the shape of the channel impulse response in order to be more to help you more actually to remove the issues, to remove inter-symbol interference. Of course, there are other ways to think of using metasurfaces to do this so-called wave computing. And now let me start providing some hints about different architectures. Up to now, we have been talking about a passive configurable RIS, meaning that you just need the power. Of course, it's not as low as expected to maintain and change the configuration of an element, which effectively provides a phase, adds a phase to the impeding signal. But you can think of ways of providing certain forms of amplitude reflection amplification, which at the end of the day enable, as you can understand, utilizing this technology to provide signal coverage even in larger distances. One of the issues that you have with passive RIS is this dual path loss effect, which of course is very relevant to this so-called area of influence, which at the end of the day, it's hard to expect that you use a passive RIS with no power there and you are able to influence a large amount of the wireless environment. Actually, the opposite holds. The passive RIS actually has a certain area of influence nearby where it makes sense to use it, and it provides performance. So let me now dig into, let's say, one of the three items that I would discuss in my talk today. The first has to do with the characterization of sub-terahertz interchannel with an RIS. And in this endeavor, we have actually fabricated, actually Sergio that introduced me before was the one that provided those static RIS prototypes at 304 gigahertz, 1-bit, 2-bit, and 3-bit phase resolution. Actually, these are static beams, but we have used, they have 3 different resolutions of actually creating a reflection from the raw side to a specific angle. This was 30 degrees specifically, as you see on the top right figure. And this actually, with these 3 metasurfaces, they have been used in one of the other partners indoor setup in order to do measurements. And in this channel sounding campaign, we have done path gain measurements. You see on the left there, where the receiver has been placed in this 30 degrees angle, but in different distances from the RIS. Although on the right, you see another set of measurements where the focus was the characterization, the analysis of the power angular profile, where you see, in this case, on a fixed distances, the TX and RX from the RIS, but rotating them in order to capture the different multipath, right, that are happening within this environment that you see in this setup. By the way, you see a plasterboard here that's separating in the power angular delay profile the direct TX to RX link in order to ensure that we have only the reflections from the input value. So in the first setup, here are a figure. You can see this paper is actually under revision in VTN. It's also available on archive, where we have actually put down the measurements for the path gain, and we have used both conventional formula for the buffers, but also a formula that we have derived within TERRAMETA, and this has been derived in the paper that we will present in the second item that we'll present in my talk. And in this figure, what the outcome, the end result is that you can see that the path gain improves with higher phase resolution. There is a 4 to 5 dB difference between the 3 bit and the 1 bit static freeze. But also another interesting thing is this empirical analysis of the near-field behavior, where we have seen that this Rayleigh distance that you see here with this DF not being as hard as expected, meaning that you could get even closer to the receiver, the actual end node, to the reach, to get actually very good performance by using the far field approximation. The gain, as you see from this figure, starts deviate at approximately 1/10, to be specific, from the thing that I said before of the Rayleigh distance, due to, of course, the near-field propagation effects. And with the formula that we have used and an appropriate adjustment, we have managed to actually accurately, as you see in these figures here, predict the path gains that we have measured in this specific setup. Now, for the power angular profile analysis, as I said before, we have actually rotated the 4 antennas at both the transmitter and the receiver to capture those angular components. And what we have seen is that we get higher phase resolution when more spatial diversity and angular spread is there in the channel, and meaning that when you have actually a RIS which is more elaborate in terms of the resolution, there provides a nicer beam. And compared with the metallic reflector, we have seen that RISs actually exhibit reduced angular spread due to the provided energy focusing that they give at the end of the day. Also, the link that was created from the main lobe of the 3-bit static RIS outperformed the natural reflections that happened from the room's walls and the floor. And we have seen overall that the results validate the capability of RISs to enable this control of both the angular diversity as well as the multipath component richness at the 304 gigahertz that we have performed. What we're working on right now is to extend those this measurement campaign by the consideration of a configurable RIS, which is being actually fabricated right now, has been designed. We're waiting for the fabrication. This is a great achievement of the TERRAMETA project by our RIS designers, and we want to investigate novel pathless modules that are adequate for low frequencies. And just to emphasize here that the main outcome of up to now this with the static RIS channel measurement campaign is that this partial approximation, as I said before, but I want to emphasize here, holds in deep near-field regions for the practical cases that we put down. Another set of activity, which is also has a certain form of correlation with that, and this is something that puzzles us a lot within the project, is how we could incorporate, since we have actually a large activity there, to try to extend an available ray tracing tool from the partner to incorporate RIS. And this is actually not a problem, and the reason for that is that we want to capture, when we're using an RIS, the varying amplitude and phases which also depend on the incident angle and the RIS configuration. So you see actually various factors that need to be taken under consideration when putting an RIS within a ray tracing tool. And the common approach up to now is to use actually idealized behavior of RISs, which of course oversimplifies the propagation model. Our goal with TERRAMETA is to be capable to incorporate the actual fabricated RISs into a ray tracing tool. On the other hand, we have the full wave simulations, which are, of course, the first tool that we use in the design and in the design within TERRAMETA RIS that you have seen there, provide a more accurate characterization of the reefs, leveraging the radar cross section patterns. However, to acquire and process all these scatter rays from the RIS certainly will overwhelm a ray tracing tool. So in this paper, with Luis and Sergio, we have studied the amount of critical rays needed to efficiently approximate an RIS performance when it is configured to beamform towards a given direction. The idea is to do it for many directions and then incorporate in a ray tracing. Here you see actually some results from a full wave simulation of a static 2-bit RIS on the frequency that we have used also for the channel measurement. And we have seen that there is a main beam, as you see on the left, that emerges on the desired angle, this theta out there, which is in green on the right figure. There is also a beam that takes place at a symmetric direction, symmetric angle, this red dust that you see on the right, and the minus theta out. And there is also a residual specular reflection, which is present, and this is the orange dust on the right figure there. Which means that at the end of the day, you have 3 dominant directions which form around of 2 degrees cones, defining the effective scattering response. And these 3 rays approximation could be actually used to be incorporated within a full wave simulation. So long story short, the proposal that we came up with this work is that the first fabricate the rays, you do full wave simulation on its behavior and specific angle. You need to do it for various angles, of course. For each angle, you get a set of the most critical beams, and these are the beams that their characteristic actually, these responses that you incorporate in the ray tracing tool in order to use this tool later on for your performance analysis of any algorithm that incorporates an RIS. Let me proceed to the other work, which is near field beam focusing with now a different type of RIS. This type is using an RIS as an XL MIMO node. These are the so-called dynamic metasurface antenna, where at the end of the day, you have again at the front end that you see on the right, on the left of this figure, the typical metasurface. But the metasurface, you have the elements grouped in a subgroup of elements placed on specific waveguides, and these waveguides being connected with either a transmitter or a receiver chain, realizing a transmitter or a receiver respectively. There have been various actually works trying to explain which are the gains in terms of power and cost efficiency compared to conventional XL MIMO architectures based on phase shifts. So, actually this work that I will present right now, it actually was a result of certain questions that we got from the channel measurements, and let me try to put them down. One is, what is the distance limit up to which far field approximation is effective for path gain prediction beam design? Number 2, what is the resolution with which the position of the beamforming target should be known for accurate beamforming in the near field? This is also called beam focusing. And another major question is how frequently we need actually to acquire CSI knowledge in order to follow a moving target with a highly directed beam without losing the focus. And of course, this depends on the QoS requirement that we have. Let me describe the system model. Here you see a DMA-based XL MIMO base station that wishes to communicate with a single user equipment, which is randomly moving within a 2D plane, as you see in this figure. And the objective of the base station is to provide beamforming towards the UE location so that the maximum possible gain is achieved at the exact position where the user is actually lying. Some things to consider here is that the UE coordinates change from the focusing position, but those changes might not affect the achievable beamforming gain, which means that in certain amount of a change of movement, we probably need to do nothing. But if we actually do, we will lose our resources, computational resources, and of course the channel by doing certain acts and knocks between the UE and the base station in order to re-establish a link which has no problem actually. Also, the resolution of the UE coordinates to be estimated could be sparser as the UE moves further away from the DS while keeping the deforming gain to the maximum. And actually, in this work, we propose to adapt both the reconfigurable time intervals between the estimation, which means how frequent you perform certain channel state information estimation, and as well as the reconfigurable localization resolution relative to the UE's current position. I will explain what is this resolution actually means. And the goal is actually now going into the mathematical analysis. We want to quantify the beamforming gain degradation due to the mismatch between the focusing and the actual position of the UE in the near field regime. For doing that, we have approximated the normalized gain loss, which is defined as the expression that you see here. The G op is the optimum beamforming gain for the specific position, and this G R hat P hat is actually the G that we can achieve by doing the specific beam focusing. We have defined with being a specific function, which is actually, as you see here, factorized by two other functions. The one is expressed as a function of the range, and the other as the angle, the azimuth angle that is needed there in the analysis that we have done. Recall that the UE is moving at the 2D plane. We can actually generalize in the 3D, and these functions quantify, as I said before, the radial and the angular mismatch. With this actually decoupled model, we have managed to get close for prediction of both the beam width and the beam depth, which are given by the expression that we see here, that this is the radial region up to which, for example, this normalized gain loss becomes larger than a percentage of the QoS that we want to achieve, and the angular region. And as you see here, there are some critical values of these delta R's and delta PKs actually derived analytically in this paper. The key insight from this figure that you see here is that we have seen that both regions, actually the region that I mentioned before, the radial and the angular, shrink as the UE approaches the base station. And also what happens is that beam width, beam depth becomes highly asymmetric. This delta RK minus depicts the direction of the UE movement towards the base station, where the actual near field effects are stronger. Hence, what it holds is that this minus version of delta RK is upper bounded by the plus version of this specific formula, this specific actually definition. Now the protocol, the QoS aware protocol, which actually uses this key notion of beam coherence time. So suppose now that you have a UE that moves for C meters, we can use the analytical model we derived before to find the direction that causes the fastest drop in the deforming gain. So imagine that the UE is getting closer to you or getting further to you, right? This is determines actually the actual protocol, how it runs. And based on this, we can compute the minimum distance needed for the gain to fall below a threshold K percentage of the maximum. And if we assume that we know the UE speed, then we can define this beam coherence time, which is a critical metric indicating the minimum time needed for the beamforming gain to drop to K percentage of G op. Actually, this is a metric that the DS can hold, right? It gets dynamically updated, which actually indicates the next timing interval where you will drop from a certain threshold, which means that again you need to ask for CSI and do this tracking, changing the beam at the end of the day. So this implies that this overall approach is a proactive QoS aware beam tracking protocol, where the base station requests pilots when these specific beam coherence time elapses, which, as I said before, is dynamically changing, thus maintaining the beamforming gain. And this overall protocol, what tries to do, and actually that does it with the results that we have presented in this paper, and ensure stable and reliable communication without actually frequent channel estimation, and it actually adapts to the near-field phenomena and different QS by means of tuning this K% that I mentioned before. In doing that, a critical aspect is this dynamic grid design that has been presented in this work, where actually we design a configurable spatial resolution for localization with the goal to find those hats, R hat and P hat, such that the gain is approximately equal to the optimum gain, and to guarantee this uniform gain of at least a certain percentage, each sampling point defines a decision area where those conditions that you see hold. By the way, what is a long story short, what I want to emphasize here is that the grid where you do the search right now, it's non-uniform and needs to be dynamically adapted while the UE moves towards any direction. And we select in this grid the minimum set of points that cover the area of influence, adaptively refining the decision intervals, which means at the end of the day that closer to the UE is the near-field phenomena are stronger, leading to shorter decision intervals. I'm not going to go into the details there. You can see details for an example in the economy of time. I will try to actually summarize here. We have provided theoretical analysis for this beam coherence time interval, which quantifies how long the deforming gain remains a certain percentage of the optimum value of our objective. In our case, it was the deforming gain. For the power allocation strategy, the BS requests pilot signals on the UE, not in every time interval, right? But on this coherence time, maintaining gain robustness during the UE motion. In doing that, we need this non-uniform grid, and the localization is based on that. It's adaptive, and the previously estimated UE positions and target gain are included therein with the certain accuracy that you see here, this delta parameter. And the iterative mechanism at the end of the day is that after each estimation, we update this beam coherence time. The same happens for the area of interest and the grid design based on the current UE position. So every time you have a different UE position which has been estimated, you recalculate all these parameters that are critical for the beam tracking protocol. Some results, the deforming gain and the estimation time. On the left axis here is the average relative deforming gain and the 95th percentile error bar over 5 milliseconds of microseconds, sorry, for time step. On the right axis, the average estimation time interval, which is the averaging there being the form of the random trajectory realizations. And what we have seen and can be seen from these figures is that by employing this reconfigurable estimation interval, the percentage of gain achieved is always greater than the K, which is an input of the algorithm. And as expected, this coherence time interval decreases as someone increases the K, which means more demanding outcome, more demanding performance, beamforming performance. Why this is happening? Because denser estimations are needed over time to satisfy this stricter constraint. Hopefully I have 3-4 minutes, Sergio, or not. Otherwise, interrupt me.
I don't actually run the show, but for me, I think we could be okay. 3-4
maybe
minutes.
5 or maybe based on the integrated communication with different RIS prototypes, which is another major activity of the signal processing actions within TERRAMETA. Just to emphasize here that thinking about passive RISs,
scenario where you can provide localization, profiting from the fact that the configurable intelligent surfaces provide additional reflections. Those reflections actually indicate diversity, new diversity that can be actually optimized in order to boost certain estimation tasks. And this is localization, right? Localization is an estimation task. Here in this figure, you can notice, if you can see the first row and the bottom row, let's say some kind of equivalences between cases where we don't have an RIS and cases where we have an RIS. And the end result is that you can enable localization by reducing the amount of conventionally needed access point in order to do that. For example, you can even think, if you see on the bottom left a case, an extreme case, where you can even localize a user with respect to the known position of a passive RIS without having any access point there, by just having the user knowing the sequence and the phase profiles that the metasurface is using. You can actually put down, especially in the wideband regime, an algorithm where you can provide localization. You can even do recent localization, simultaneous localization, and radio mapping, again by not having any RIS, any access point, again by profiting from the fact that you have an RIS synchronized with a UE, and you can actually provide localization with respect to the RIS. And the only thing that the UE needs to know is that the beams that the RIS is using. So imagine a UE that gets the beams that the RIS is having and actually collaborates with it. I mean, get synchronized. Only this is needed in order to find each position with respect to it, but also to do a sort of mapping of the scattering objects that are within the vicinity that this actual pilot signal transmission will impact. But let me also try to emphasize another activity within TERRAMETA. This is the so-called hybrid RISs, where hybrid RISs, there are certain ways of thinking of them, but at the end of the day, they want to provide simultaneous reflections, but also enable certain form of estimations of the signals that are impinging on them. There are different hardware architectures. The one is to embed on a conventional passive RIS sensors, or let's say dedicated antennas that are doing receptions, or using hybrid beta atoms, unit cells that can simultaneously reflect a portion of the impinging signal in a tunable way, while the other portion being driven through waveguides in actually units that we can actually provide measurement of this impinging the portion of the impinging signal. It could be, for example, reception RF chains, and you could envision of a baseband actually unit that performs the estimation directly in the baseband of those received portions of the impinging signal. As I mentioned before, you can even think of interleaving actually conventional antenna arrays within a metasurface to provide this dual fractionality. I'm not going to dig into the details here. You can see these papers of this way of realizing through substrate integrated waveguides, actually elements that are hybrid, and they can do this simultaneous operation. Let me actually, this last part, to present with this specific hybrid RIS, a way to provide simultaneous communication. You see a UE within the environment, but also localization coverage within an area of inference. So in this system model, what is being done is that there is a base station, there is a hybrid RIS. The hybrid RIS has the dual role to enable a downlink communication between the base station through its reflection parts, reflection capability with the UE, but also it wants to profit of the reflections that will come from the downlink signal that will come from targets within a certain area of influence being received at the hybrid RIS and profiting from its reception estimation capability to try to localize where are these users are. Where are these users within the system? So in a way, the sensing, the receiving portion of the RIS together with the base station, they operate like a bistatic radar only through data signals, not dedicated pilot signals. In the economy of time, you can see the details in this fresh UCAP paper. This is also available on archive as well. The reception part of the RIS is being modeled as a DMA-like dynamic metasurface antenna receiver, where you have it's like analog combiners at the end of the day, where we have used models for the included unit cells. Of course, there are certain works right now in extending, incorporated all the losses that happen within the waveguide, and we have used actually a near-field channel model to put down the estimation algorithm, the estimation analysis and algorithm. A typical near-field channel model, which in the economy of time I'm not getting into the detail. And there you see the received signal, and there is this critical row or parameter which actually determines the amount of the signal that gets absorbed, directed in the baseband the microcontroller of the RIS to perform the estimation, and the other portion that gets reflected. In this paper, we have provided a position error bound, and long story short, this is all the story. Before I finish, we want actually to maximize the downlink rate, and with respect to the configuration, the receive configuration of the hybrid RIS, the reflection configuration of the RIS, but also the transmit precoding at the base station, having constraints that has to do with the position error bound on a grid amount of position. This is the discretization of the area of influence where we want to provide coverage, and constraints that have to do with the transmit power and the actual hardware characteristics of the RIS. I don't have time, so it's doable. You can provide an area-wide PEB in order to enable actually this pi-static sensing of the target. Of course, there is a trade-off between the achievable rate and the localization coverage, and this definitely depends on how accurate you want your localization to be, which means on this bound that I showed you before, on the position error bound, and of course also depends on the ROTA parameter, the amount of signal that gets reflected or gets directed to baseband for estimation. So Sergio and all, I would like to thank you for your attention. Looking forward for any question if there is time.
Okay,
thank you.
Thanks a lot. So I don't know if there's any question. Maybe we are running out of time. Maybe we can go to merge the final discussion with this Q&A. Maybe now I'm not supposed to share this part, right?
Yes,
Okay.
it will be myself, but we are already 5 minutes late, so 7 minutes late. So if there are some questions about George's presentation, otherwise I think we have to close.
Yeah. So I have a question if nobody else, because this configuration of this Isaac, where you basically have this hybrid solution for reflecting and receiving, you present two options where you basically interleave, or you simply have a cell that operates simultaneously as receiving in transmission. So of course, it will be only a portion of the energy that will be absorbed for sensing. So maybe there is still a hybrid thing where you can actually use the switch of the RIS to actuating parts of the surface, and this could be dynamic, to make them as instead of reflecting unit cells, transmissive unit cells. So instead of being simultaneously, you take parts of the aperture and make them transparent, so you can read the signal, and then this could be actually programmable as well. So I don't know if this is a stupid idea or something that
No. Sergio, it makes total sense, because at the end of the day, yeah, if you use, let's say, the hybrid version, right, what you receive, it has this penalty of have this raw parameter, right? Because you want also to simultaneously reflect, which means that at the end of the day, you have a lower SNR on the received signal that you use for the estimation. Though if you do what you propose, you have, let's say, the highest SNR that you could do, and this could improve your estimation. So there are certain optimization there that need to be, of course, taken under consideration, given on the setup that you want to place the RIS, and given on the area that you want to be able to provide this sensing capability. Of course, you would do, as you said before, the extreme ways to do it on a switching basis, right? Meaning that you have you use it, let's say, for certain time intervals to fully reflect, and for other intervals to fully absorb, right? So you don't penalize in terms of SNR any of the two operations by trying to do things simultaneously.
But you can
So
even
what you said
split
makes sense.
you can even split the aperture because you can still do simultaneous, but with less area for transmitting or receiving. So it would be switching from transmissive to reflective RIS, but you can actually do two subarrays, one acting as a transmissive, the other as a reflective, and the area of each one could be dynamically controlled. So this could be interesting degree of freedom.
Exactly. Exactly. I think it's interesting. You know, this is an idea we have within the TERRAMETA. It's, I think it's totally open for, you know, various configurations from the hardware perspective, being, of course, co-designed with signal processing in order to have a system that operates, as you said, dynamically. I think this is very interesting.
So let's talk. Okay, thanks.
Thank you.
Okay. So I think that we can close the workshop here, and I would like to thank all the speakers for the very nice presentations, and also the organizers of Gilberto, Luis, and Sergio for being here, chairing the sessions, and be active for the questions. So thank you all, and I hope that there will be a third edition for this workshop. So have a nice day.
Paolo, thanks for all the organization. It was great.
Thank you. Bye.
Bye-bye.
Thank you. Bye.
Thank you. Bye bye.
Bye.